Okay, so in this lecture, we are going to look at power series. We are finished, completely finished with module 7. We are in the home stretch. We are in the last module, which only has 3 topics, and the first of which is power series. In this section, we're going to identify what a power series is and provide some examples of them. Determine the radius of convergence and interval of convergence of a power series, and use a power series to represent a function. So we're only going to be talking about specific types of functions for this particular power series, and then we'll go on to more power series representations of functions in section 6.2 and 6.3. Okay, so what is a power series? So okay, hold on a minute. Oh, I'm using the wrong pen. That's why. Trying to figure out why my pen doesn't work. I'm using the wrong pen. Okay, so a power series is a series of the form summation n equals 0 to infinity of C sub n x to the n. Okay, so it looks like C0 plus C1x plus C2x squared plus C3x cubed. And here, Cn are specific constants. Are constants for each n. Okay, so this form of power series is about x equals 0. Okay, so we can also talk about a power series about x equal to a. In other words, that means it's going to be centered at a. Is of the form summation n equals 0 to infinity of Cn times x minus a to the n. Okay, so this is a power series about x equals a. All right, so some examples. Summation n equals 0 to infinity of x to the n over n factorial. Well, here we're going to take 0 factorial, as I told you before, has to be defined to be 1. So this is going to be 1 plus x to the first over 1 factorial plus x squared over 2 factorial plus all the way up to x to the n over n factorial plus dot, dot, dot. And this is a power series. Again, this one is about x equal to 0. Another example, sum n equals 0 to infinity to the n over n factorial x minus 1 to the n. So this would be 2 to the 0, which would be 1 over 1 factorial, so that's 1, plus the second term would be 2 times x minus 1 to the first power. And the next term would be 2 squared over 2 factorial times x minus 1 squared plus 2 cubed over 3 factorial times x minus 1 cubed plus ... Okay, they can get even more difficult. You can have the sum n equals 0 to infinity minus 1 to the n plus 1 x minus pi to the n over 2n plus 1 factorial. Okay, so this power series is centered at x equals 1. And here, a is equal to pi. And in the first one, a is equal to 0. Okay, so what does it mean for a power series to converge? Well, it's just like any other series. Okay, so when a power series converges, that just implies that the sum n equals 0 to infinity of Cn, whatever that is, x minus a to the n is some finite number. It does not blow up to infinity. So now we've looked at some series. We looked at 12 different series tests, okay, to determine whether or not specific series converged or diverged. Okay, and so we can talk about the power series converging or diverges. Okay, so we're going to consider this power series. Okay, so we want to say one of three things happens. Okay, all right, so the first one, that is the series converges at x equal to a and diverges for all x not equal to a. Obviously, if I put in x equals a, I just get 0 to the n. So I'm adding up a bunch of terms that are 0 with the exception of the first term. And so therefore it's going to converge. Okay. The second thing is the series converges for all x that are real numbers. So every real number, no matter what x is, it's going to converge. or it's going to have a region that it can converge in, and we call that region an interval of convergence. And so we're going to say there exists some positive real number R that's greater than 0, such that the series converges whenever the absolute value of x minus a is less than some number R, and B, the series diverges whenever the absolute value of x minus a is greater than R, and then C, you have to check when the absolute value of x minus a is actually equal to R. Okay, so what it looks like is right now, we already say, I'm gonna draw a number line here. So right at, here's x equal to a, okay? So the first case is it only converges at a, okay? So the first case is the only place it converges at a, all right? And then it diverges everywhere else. So that was case one, okay? Okay, in case two, it converges everywhere. So case two, the series converges for all x. So here's A. Okay, so this is case two. And then the third case, here's A. And then there's some interval. Well, let's see, what is that interval? What does it mean for the absolute value of x minus a to be less than R? Then that means that minus R is less than x minus a is less than R. So then I can add a to both sides. So I get a minus R is less than x is less than a plus R. So this point right here is going to be a minus R. And this point right here is going to be a plus R. And I'm going to get it converges in this spot, just there. But I have to check everywhere else, and it diverges everywhere else. So here and here, it's going to diverge. And this is case 3. So what we're going to have to do is determine when these power series converge and the interval of convergence. Okay, so for any particular power series, it's a series. So therefore, since it's a series, we can use our previous series tests in order to determine when and where it converges. Okay, so let's look at the first one. Determine the interval of convergence. For the following series. Okay, well, the first one is going to be rather easy. So I'm going to let the first one be the sum n equals 0 to infinity of x to the n. Okay, well, this series is 1 plus x squared plus x cubed. So that should look familiar to you. That series, if you remember, is the sum n equals 1 to infinity of x to the n minus 1. So this is just a geometric series. And so we said for the geometric series, we said this converges if the absolute value of x is less than 1. So here the radius of convergence is going to be 1 because this is about x equals 0. So this is a power series. And so we're going to get minus 1 less than x less than 1. So the radius of convergence is 1. And the interval of convergence okay. Okay, so here's one. Number 2, summation n equals 0 to infinity x to the n over n cubed 4 to the n. Okay, so just in case you don't see it, Cn in this problem is 1 over, oh, this one has to start at 1. This one can't start at 0. It has to start at 1. Okay, so this is n cubed 4 to the n. All right, so one of the main tests that you can use for convergence of power series are the root test and the ratio test. So let's use the root test on this. So if I use the root test says compute rho equal to the limit as n approaches infinity of the nth root of the absolute value of an. Now, we know, so we know from the root test that the series converges if rho is less than 1. Okay, so we know if rho is less than 1, the series converges. Okay, so that means in order for me to find convergence, I need to find all the places where rho will be less than 1. So let's compute rho. So the nth root of the absolute value of an so the absolute value of an is going to be the absolute value of x to the n divided by n cubed 4 to the n. So now if I want the nth root of that, that's basically going to take the absolute value of an and raise it to the 1 over n power. So therefore I get the nth root of the absolute value of an is simply the absolute value of x to the n divided by n cubed 4 to the n to the 1 over n power. So that's just going to give me the absolute value of x over n cubed to the 1 over n times 4. Because the 4 to the n to the 1 over n just gives me 4. And I can then write this as the absolute value of x over n to the 1 over n cubed times 4. So we're in good shape. So therefore rho is going to equal the limit as n approaches infinity of the nth root of the absolute value of an, but that's just the limit as n approaches infinity of the absolute value of x over 4 times n to the 1 over n cubed. And luckily we remember that n to the 1 over n goes to 1. So this just becomes the absolute value of x divided by 4. The limit as n approaches infinity of n to the 1 over n is 1. So now we need rho to be less than 1. So that implies then the absolute value of x over 4 has to be less than 1, which implies the absolute value of x is less than 4. So this thing becomes our r. So r, interval, so the radius of convergence r is equal to 4. And our interval, oh, that's the radius of convergence. Yes, interval of convergence. Well, for the interval of convergence, we need to check to see what happens. So okay, let me actually erase this first. So my interval of convergence, let's start off with the simple interval of convergence. The simple interval of convergence is -4 less than x less than 4. And so now we need to check our endpoints. Now, why didn't we need to check the endpoints of the first series? Well, because the first series was a geometric series, and we already know that it doesn't converge at 1 or -1. That we know. But this one, we have to check to see what's going to happen at our endpoints. Okay, so we're not done yet. So we know it converges inside that interval. Let's see what happens. So at x equal to -4, we get the sum n equals 1 to infinity. We get -4 to the n, or -4 to the n over n cubed 4 to the n. And that looks like the sum n equals 1 to infinity of -1 to the n over n cubed. Okay, because I take and I can make that just -1 to the n. All right, so now does this series converge? All right, well, this is an alternating series. So for this one, I'm going to have to use the alternating series test. So let's see. Want to let un equal 1 over n cubed. All right, and that's always positive. 2, since n is less than n plus 1, n squared, n cubed is less than n plus 1 cubed, which then implies 1 over n cubed is greater than 1 over n plus 1 cubed. So un is bigger than un plus 1 for all n. So it satisfies the third thing, and the limit as n approaches 0 of 1 over n cubed is 0. So by the alternating series test, summation n equal 1 to infinity of minus 1 to the n over n cubed converges. Okay, so that lets me know I need to include -4. Okay, so now let's see what happens at x equal to +4. Now we have the sum n equals 1 to infinity of 4 to the n over n cubed times 4 to the n. And this is just the sum n equals 1 to infinity of 1 over n cubed. And I can say that converges by what? Why can I say that converges? What does this series do? It converges. Why? Are y'all still here? Okay, I have 16 participants. Nobody wants to answer my question? Not even in the chat? Don't make me pull out my wheel.
Does it converge by the alternating series test like the previous one?
Okay, that is a good answer. But this series is not alternating. This series has a form. What form?
P series.
Okay, that's the P series. So now this says I must include 4. So now I can readjust my answer. My interval of convergence is now -4, less than or equal to x, less than or equal to 4. Okay, any questions about that? Okay, we'll find out. Here's number 3. Let's do this one. Okay, so since I have an n factorial, I'm going to use the ratio test. Here, an is x to the n over n factorial, and an plus 1 is x to the n plus 1 over n plus 1 factorial. So now for the ratio test, for convergence, rho equal to the limit as n approaches infinity of the absolute value of an plus 1 over an has to be less than 1. So that's the ratio test. Okay, so let's compute rho. So I'm going to get the absolute value. So I'm going to get x to the n plus 1 over n plus 1 factorial. And I'm going to divide by the reciprocal, well, multiply by the reciprocal, which is going to give me n factorial over x to the n. So that's the limit as n approaches infinity. Well, x to the n plus 1 over x to the n is just x, but it's still an absolute value. And n factorial over n plus 1, well, that's positive. Well, that limit, no matter what x is, that limit is 0, which is always less than 1. So that implies the radius of convergence is infinity. And the interval of convergence is minus infinity less than x, less than positive infinity. Summation n equals 0 to infinity of n factorial over 10 to the n x minus 2 to the n. So this power series is centered about x equals 2. I'm going to use the ratio test. So an is n factorial over 10 to the n times x minus 2 to the n, and an plus 1 is equal to n plus 1 factorial x minus 2 to the n plus 1 divided by 10 to the n plus 1. So rho equal to limit n approaches infinity, the absolute value of an plus 1 over an is going to be the limit as n approaches infinity of n plus 1 factorial x minus 2 to the n plus 1 all over 10 to the n plus 1. Divide by an is going to give me 10 to the n. Over n factorial x minus, no, 10 to the n. Yep, that's right. Okay. So now I'm going to simplify this and I'm going to get the limit as n approaches infinity. So I'm going to get n plus 1 in the numerator. I'm going to get 10 in the denominator. And I'm going to get x minus 2 in absolute value in the numerator. Now, if x equals 2, then this limit rho is simply equal to 0, so it'll converge. But if x is not equal to 2, then rho is equal to infinity, and it diverges. So this is the case where it only converges at A, but nowhere else. Okay, so we've seen a couple of different things here. The first one, because it was the exact geometric series, we knew what the radius of convergence was, and we know it doesn't converge at 1 and minus 1. I think I have chat. Okay, good. Okay. Then in the second example, we fixed it so that rho being less than 1 meant that absolute value x over 4 is less than 1. So that was less than 4. That's the second example, yes. So therefore, we got this is a preliminary interval of convergence. Why don't I call it that? Because we really have to check. We're not done until we check the endpoints. And so we check the endpoints by just plugging in -4, seeing what that series looked like, and +4 and seeing what that series looked like. So we got a conditional region or interval of convergence. Then for problem 3, we saw that it converged everywhere. And then in problem 4, it only converges at A. Okay, so one last thing I want to do. I forget, I have 6 more minutes. Okay, so can we find the power series for some functions? Easily. And the answer to that is yes. So let's think. So let's take this function, f of x, equaling 1 over 1 minus x. We know that that is the convergent power series, sum n equals 0 to infinity. of x to the n, because the summation n equal 1 to infinity of x to the n minus 1 is equal to 1 over x, 1 minus x, when the absolute value of x is less than 1. So, therefore, this is true for the absolute value of x less than 1. How about this one? F of x, let's call it g of x. I'll give it a different name. G of x equaling 1 over 1 minus x squared. Okay. Well, let's think. I think that's simply going to be the sum n equals 0 to infinity of x squared. I don't need the absolute value. Of x squared to the n. So this is the sum, n equals 0 to infinity of x to the 2n. Again, if the absolute value of x squared is less than 1. With that just says the absolute value of x is less than 1. How about h of x? One over 1 plus 2x. Okay. Well, if this is going to be what I said before, if this is actually equaling 1 over 1 minus r, or a over 1 minus r, where a is 1, that implies then that r has to be minus 2x. Okay, so if r is minus 2x, and that says h of x being 1 over 1 plus 2x is equal to the sum n equals 1 to infinity of minus 2x to the n. Or the sum, and this should be 0, n equals 0 to infinity minus 1 to the n times 2x to the n. And when is this going to converge? Well, it's only going to converge when the absolute value of r is less than 1. So this converges when the absolute value of minus 2x is less than 1, or the absolute value of x is less than 1/2. Okay, now, do you guys have an exam tomorrow? I know, yes, you do. Okay, so you have an exam on module 7 tomorrow. I am available tomorrow at 12 o'clock for office hours for anybody that wants to come.